In this example, we're going to show about the growth expression. If you remember, previously I've already made an example about population growth. So please try to see that example again in our previous videos. Right now, I'm going to focus more on the estimation of reserves like fossil fuel or even renewable energy reserves in the future. So to estimate the reserves, we have two kinds of approach. The first one is at constant energy demand, and the second one is with a growth in demand. So when you say constant demand, it means that the demand doesn't change year after year. So we can use this formula here. T sub s is equals to F over A, where T sub s is the time until the reserve is finished or exhausted. The F is the energy reserve. It means the what is remaining reserve at this point in time. And A is the annual demand. So the annual demand is the same year after year. It's constant. So we can use this one if we have a constant energy demand. If we have a growth in demand, like every year it's changing, it's growing, more and more people. So most likely in terms of what is happening, there is always a growth in demand because of the growth in population as well. So we can use this formula. F is equal to A times the product of this one, the result of this one, so which is parentheses 1 plus I raised to the n minus 1 over I. So F and A is the same here. This is the current energy reserves. A is the annual demand, plus I is actually the annual increase in terms of how much percentage increase year after year. And N is where the number of years to consume the reserve. It should be small n here. So this is a number of years. So how many years will we consume the reserves? Okay, to better understand how to use this formula here, we'll take a look at our example. All right, so our example is this one. The coal consumption in 2004, in year 2004, was 120.8 exajoules. So this 128 exajoules, if you make it into joules, times 10 to the 18th joules. It's the same. So exajoules is 10 to the 18th. Assuming that the energy demand from 2004 remains constant, estimate how long will the reserves last if we have a constant annual demand. Letter B, that's letter A. Letter B is from 2000 to 2004, the average world coal-based energy consumption increased by 5.15% per annum every year. It's increasing every year. If that rate remains constant, how long will the world coal reserves last? So if we have a constant growth in rate, and then how long will it last? And for that year, for example, we say for those years, the world coal reserve was 19,800 exajoule. So this was the remaining coal reserve at that year. Okay, so let's try to see each one. So the letter A, the given was coal consumption. There's coal consumption. Right, so which is equal to 128.8 exajoule. And then we are also, okay, that's the given, and the other given is the coal reserve. So world coal reserves. So which is equal to 19,800 exajoules. So since the units is the same, so we can just use directly. So based from this formula here, T sub S is equal to F over A. In this case, F is the reserves. So 19,800 exajoule over the annual demand, energy demand, constant exajoules. So cancel this one is equal to, this is per year, yeah, per annum. That's per year. So it means that with this one, we can say the total number is 163.91 or 164 years. So if we looking from this example at an annual constant demand, we have a lot of years left. more than going towards 200 years of goal. But if we consider the annual growth of 5.15%, so basically there's an additional given here in letter B. So the annual growth, which is I, is 5.15%, right? So that's the annual growth. So the question now is, how long will it last now with a growth of 5.15% every year? So let's use this formula now. F A times this term, 1 plus I to the n minus 1 over I. Okay, so what is F? F is already given, which is the same as the other one here. So, okay, I'll just put something here. So this is F, okay, and this is A, and this first point. So our A is the same here in our the last one. So F is 19,800 exajoule. All right, and then A is basically 120.8 exajoule, and then 1 plus what is the annual growth now is 5.15%. So this one is 0.0515 over to the n, okay, minus 1. And then this one is also 0.0515 because this is the I and this is also I here. Okay, so based from that we can solve for n. This one is what we are trying to solve on. So how do we solve this one? So we can solve this one by, okay, we can arrange this one now. So what we can do is basically we have the 19,000 over 120, right? So we can also put this one down. So 19,800 exajoule over 120.8 exajoule, okay, per year times 0.0515 is equal to, so what happens now is what is remaining. So what is remaining now is this one we can add. So that's 1.0515 to the n minus 1, right? Okay, so let's continue. Okay, so we can put it here. Okay, I hope we have enough space. So we know that this part is basically this one here. All right, so we have 163.91 times 0.0515. Okay, then all of this should be, because we can transport this one into the other side, so plus 1 is equal to 1.0515 raised to the n. And so with that we can now solve for all. So it becomes 9.44 is equal to 1.0515 raised to the n. Okay, and then we can log it. Yeah, we need to solve for n. So log 9.44 is equal to how do we solve for the log? So if that's the case, we can also log this one, this side here. Okay, so it becomes n log 1.0515. In this case, we solve for the log here, and n is equal to 44.7 years or 45 years. Okay, so I hope this is still clear at this point here. So we have two answers now. The other one is 164 years and the other one is 45 years. So you can see that, of course, there's a difference in terms of the number of years of exhaustion because of the increase in the growth. There's a growth rate here, while on the other side is a constant. So that's the effect of the growth rate.